Good morning, weather enthusiasts. Today forecast take us on another journey to unravel the celestial mystery of oxidation through the both of classical and electronic lenses. So let's brace ourselves for an electrifying experience. Classical oxidation is like a dynamic dance where elements swells with oxygen or electronegative partners. Picture this. As oxygen sloops in, it bonds with atoms, forming new compounds and bringing a burst of freshness to the reactions. Electronegativity also elements join in this captivating calligraphy, embracing their electronegativity as they team up with other atoms. Our weather analogy, just like a refreshing gas of air on a warm day, classical oxidation revitalizes chemical system, transforming substance and creating a fascinating energy charge. Keep an eye of this brilliant process in the atmosphere. You might just witness the magic of classical oxidation in action. Now, let's dive into the rhythm of electronic oxidation, where atoms and ions play a thrilling game of electrons loss. Picture ions reluctantly parting with their electrons, like stars surrendering their shimmering light. This loss of electrons brings about exciting transformation, alternating the chemical of our surroundings. In our weather forecast, electronic oxidation might be like a spark in the sky, where ions release their electrons, generating flashes of energy and making way of new chemical reaction. It's an electrifying phenomenon, shaping the delicate balance of charges and adding a mesmerizing glow to the atmospheric theater. Ladies and gentlemen, I'm Kabayan Jims, and today get ready for the exciting weather forecast like no others. Today we dive into the capacity world of celestial chemistry, where redox reactions shape the every fabric of our existence. Buckle up as we unravel the mystery of oxidation, and now let's unravel the enigmatic wonders of reduction. So, in the realm of celestial chemistry, reduction takes center stage, and we will explore this phenomenon through two fascinating lenses, the classical and electronic concept. So picture this: classical reduction, a mesmerizing dance where elements will pair with hydrogen and or electropositive partners. As hydrogen joins the mix, it gracefully bonds with the atoms, bidding farewell to other electronegative elements. It's like adding a touch of humidity and certainty to the chemical composition. Just like a gentle rain that nurtures the earth, classical reduction nourishes the chemical system, creating a harmonious balance and transforming substance in the process. Now, let's shift our focus on electronic reduction, where atoms and ions eagerly embrace the role in the grand dance of electrons. Imagine ions reaching out like stars really yearning for the shimmering light. It's like this is a trailing process where they gain electrons alternating their charge and creating a brilliant display of energy. So our weather analogy, it's like visiting a spectacular lighting show as ions drain their electrons and electrifying energy surge through the atmosphere, setting the stage for new chemical reaction.
Smart Sound.
Alright, weather forecast time is up. Now, it's time to dive into the captivating world of classical idea of oxidation and reduction reaction. Our knowledgeable guide, Kuya Yuri, will take us to the enlightenment journey as he explained the essence of oxidation and reduction. Thank you, Kabayan James. So, I'm Kuya Yuri and today I will gonna explain to you the classical idea of oxidation and reduction reaction. So, in oxidation and reduction reaction are fundamental chemical process that involve the transfer of electrons between reactants. So, in those reactions, some substance lose electrons where they undergo oxidation, and while others gain electrons that they undergo in reduction. So, oxidation reaction, so it involves the following process. So, addition of oxygen, for example. So, in this step, substance combine the oxygen, example, carbon combined with oxygen to form carbon dioxide. So here we can see their reaction where it become a carbon dioxide. Now we have also addition of electronegativity elements where here a substance react with electronegativity elements. One with high affinity for electrons. For example, we have iron here where react with sulfur to form iron sulfide. Next, we have a removal of hydrogen. So this step involves the removal of hydrogen from the compound. Example here is hydrogen sulfate react with bromide to form hydrogen bromide and sulfur. And then lastly, we have also here removal of electropositive elements, where in this process electropositive elements, those with tendency to lose electrons, for example, are removed from the compound. Example for this is potassium iodide that react with hydrogen peroxide to form iodine and potassium hydroxide. So we also have here oxidating agent. So oxidating agent is a substance that facilitates oxidation in a chemical reaction. In the provided example, we have O2, S, and Ci2, and Br2 and H2O2 that act as an oxidating agent because they help in the oxidation of other substances. Now let's talk about the reduction reaction where it involves the following process. So here we have addition of hydrogen. So here a substance between hydrogen atoms. So example, nitrogen react with hydrogen to form ammonia. Now we also have here the addition of electropositive element. So in this step involve the addition of electropositive elements, which is one with a tendency to donate electrons. For example, the tin react with mercury chloride to form sonic chloride and mercury chloride. Alright, now we move on to the removal of oxygen. So in this process, oxygen is removed from a compound. Example for this is zinc oxide react with carbon to form zinc and carbon monoxide. Alright, now let's move on to the removal of electromagnetic elements. So here, an electronegativity elements is removed from a compound. Example, ferric chloride react with a hydrogen to form ferrous chloride and hydrogen chloride. So also here in the last part, we also have here the reducing agent. So when we say reducing agent, is a substance that facilitates reduction in a chemical reaction. In the provided example, we have H2, Hg, Ci2, and C act as a reducing agent because they help in the reduction of other substance. Remember everybody that the key concept to remember this is that a substance undergoing oxidation acts as a reducing agent, and a substance undergoing reduction acts as a oxidizing agent. So this is because the reducing agent donates electrons and causing the reduction to another species, while the oxidizing agent accepts electrons, causing the oxidation to other species. Alright, now let's talk about the oxidation and reduction in terms of electron transfer. So the image show a diagram of oxidation and reduction in terms of electronic transfer. The diagram shown here is the step involved in the oxidation reduction reaction, which is a type of chemical reaction that involves the transfer of electron between two species. So the first step in the diagram shows a molecular of zinc that has lost 2 electrons. This is an oxidation reaction because the zinc atoms has lost electrons and become oxidized. The electrons that were lost by the zinc atoms are transferred to molecular of sulfur, so which is reduced in the process. So the second step in the diagram shows the zinc atom and the sulfur atom as ion. So the zinc ion has a +2 charge because it lost 2 electrons. Now the sulfur ion has a -2 charge because it's gained 2 electrons. The third step in the diagram shows that the zinc ion and sulfur ion combining to form a molecular of zinc sulfide. This is the end of product of oxidation and reduction reaction. So in summary, the image shows the step of involved of oxidation reduction reaction. Oh, that's so fun. In terms of electron transfer. So the zinc atoms is oxidized in the process, while the sulfur atoms is reduced. The end product of the reaction is a molecular of zinc sulfide. Now let's talk about common redox reaction. So we have 3 types of common redox reaction. So we have combustion, disprotonation, and single replacement reaction. So let's start with the combustion reaction. So these are the type of redox reaction that occurs between a compound and molecular oxygen. So in a combustion reaction, the compound is oxidized, meaning that it's lost electrons and gain oxygen. The oxygen is reduced, meaning that it gains electrons and lose oxygen. So the product of this combustion reaction are typically carbon dioxide and water. Now let's move on to the disprotonation reaction. So these are the type of redox reaction where a single reactant is both oxidized and reduced. So this means that the reactant lose electrons in one part of reaction and gain electrons in another part of reaction. So disprotonation reaction are often used in the product of chemical. Next, we have a single replacement reaction. So these are the type of redox reaction that involve two elements switching place within a compound. In a single replacement reaction, one element is oxidized and another element is reduced. The oxidized element lose electrons and the reduced elements gain electrons. So single replacement reaction are often used in the purification of metal. So let's discuss each example of 3 types of redox reaction. So here in the combustion reaction, we have the reaction of hydrocarbon is classic example of reduction reaction. So in this reaction, the hydrocarbon is oxidized to carbon dioxide and water. So the carbon in the hydrocarbon lose electrons and gain oxygen, while the oxygen in the oxygen molecules gain electrons and lose oxygen. The product of this reaction are carbon dioxide and water, which are both oxidized compounds. So as you can see in this equation, the oxidation state of carbon in the octane change from -2 to +4 or +4, and the oxidation state of the oxygen in oxygen change from 0 to -2. So this is showed that the octane in oxidized and oxygen is reduced. Now let's go to the disproportion example here. So as I said, disproportionation reaction is a type of redox reaction where a single reactant is both oxidized and reduced. So this means, just a quick recall, so this means that the reactant lose electrons in one part of the reaction and gain electrons in another part of the reaction. So disproportionation reaction are often used in production of chemical. So we have the example here of hypochlorine ion. So in this reaction, the hypochlorine ion is both oxidized to chloride ion and reduced to chloride ion. So the oxidation state of chlorine in the hypochlorite ion change from -1 to +5 in chloride ion, and it changed from -1 to -1 in chloride ion. So this shows that the hypochlorite ion is both oxidized and reduced in this reaction. Okay, now last we have here the single replacement reaction. So let's have quick recall lang. So pag sinabing single replacement reaction, it's type of redox reaction that involve two elements which replace within a compound. So it has one element that oxidized and another element is reduced. So we have a example here of single replacement, which is the zinc metal with hypochlorite acid. So in this reaction, the zinc metal is oxidized to zinc chloride and the hydrogen gas is reduced to hydrogen gas. The oxidation state to zinc in zinc metal change from 0 to +2 in zinc chloride, and the oxidation state of hydrogen in hydrochloride acid change from +1 to 0 in hydrogen gas. So this is show that the zinc metal is oxidized and hydrogen gas is reduced in this reaction. Now last but not the least, let's try to compare and contrast the oxidation and reduction. So oxidation is the loss of electron during a reaction. The oxidized species is called the reducing agent because it reduces the other species in a reaction by giving up its electrons. Meanwhile, in reduction is a gain of electrons during a reaction. The oxidized species is called the oxidizing agent because it oxidizes the other species in the reaction by taking its electrons. So a redox reaction is a type of chemical reaction in which oxidation and reduction occur at the same time. This reduced species receive electrons from the oxidized species and the oxidized species lose electrons to the reduced species. The term oxidation does not necessarily mean that oxygen is involved in the reaction. In fact, many oxidation reactions do not involve oxygen at all. For example, when a metal reacts with acid, the metal is oxidized and the acid is reduced, even though no oxygen is present. Alright, so let's summarize all the discussion we discussed so far. So originally, the term oxidation was used to describe reaction where elements combine with oxygen. For example, the oxidation of magnesium involved the chemical reaction between magnesium metal and oxygen to form magnesium oxide. The word reduction comes from the word to lead back, or sense of the Latin stem. Thus, everything that leads back to magnesium metal in the previously mentioned chemical reaction imply reduction. An example of reduction of magnesium oxide to magnesium metal is a reaction between magnesium oxide and carbon at 2000 degrees Celsius to form magnesium metal and carbon monoxide. Due to the change of oxidation state that occur without the independent transfer of electrons, many reactions in organic chemistry can be classified as redox reaction. For instance, oxidation state of carbon atoms in the wood increase during a combustion of wood with molecular oxygen, and that of oxygen decrease as carbon dioxide and water are produced. So the oxygen atoms are reduced, formally receiving electrons, while the carbon are oxidized, losing electrons. Therefore, oxygen is the oxidizing agent and reducing agent in this reaction is carbon. So that's all, and thank you for listening. Hello there, I'm Kuya Yuri, and today we're gonna discuss the oxidation number. So in simple terms, it's like a special number given to elements when they share or join together in a chemical mix. It's all about how many electrons those atoms can share, lose, or gain when they make chemical bonds with atoms of other elements. So, what is really the oxidation number? It is enough to introduce it, so let me explain it furthermore. So, the oxidation number is a hypothetical charge that an atom appears to have forming ionic bonds with other heteroatoms. An atom having a higher electronegativity when even its form or covalent bonds is assigned a negative oxidation state. The definition of oxidation number assigns oxidation state to an atom on two conditions. So, first is the atom bonds with heteroatoms. The atoms always form ionic bonding by either gaining or losing electrons or irrespective of the actual nature of bonding. Since an atom can have multiple valence electrons and form multiple bonds, all of them will be assumed to be ionic and assigned an oxidation state equal to a number of electrons. Now, involving in bonding. So, that oxidation number or state is a hypothetical case of the assumption of atoms forming an ionic bond. The maximum oxidation state exhibited by an atom is 10. This is seen in a complex of cation of platinum, where platinum has an oxidation state of 10. So this means that platinum has lost 10 electrons to form the ion. However, the ionization energy required for removing an electron for positively charged species increase heavily with decreasing charge. So, the removal of 10 electrons is highly hypothetical. Similarly, the addition of electrons also becomes difficult with increasing negative charge. So, oxidation state larger than 3, whether positive or negative, are practically impossible. In spite of the assumption that oxidation state larger than 3 are impossible, is it still a useful concept for understanding the charge of uncoupling the atoms undergoing a chemical change. For example, the oxidation state of atom can be used to determine whether it has been oxidized or reduced in a reaction. So, here are some additional points to consider. 1. The oxidation state of an atom can be positive, negative, or 0. 2. The sum of the oxidation state of all of atoms in a molecule or ion must equal 0. Oxidation states are useful for assigning names of chemical compounds. And lastly, oxidation state can be used to track the transfer of electrons in a chemical reaction. Let's move on to how to find the oxidation number of an atom. So, the oxidation number of the atom or ions is the number of electrons an atom or ion has either gained or lost compared to the neutral atoms. Now, electropositive metals atoms of group 1, 2, and 3 lose a specific number of electrons and always have constant positive oxidation number. So, in molecules, more electronegative atoms gain electrons from less electronegative atoms and have negative oxidation state. The numerical value of the oxidation state is equal to the number of electron loss or gain. For example, in a molecule's H2O, the oxidation number of hydrogen is positive 1 and the oxidation number of oxygen is negative 2. This is because hydrogen has lost 1 electron to oxygen and oxygen has gained 2 electrons from hydrogen. The oxidation number of an atom or ion in a molecule or ion can be assigned by the following those rules. Okay, so the oxidation number of the free element is 0. The oxidation number of monoatomic ion is equal to the charge of the ion. The oxidation number of hydrogen is positive 1 in a most compound, but is it negative 1 when bonded to a more electronegative element such as fluoride. The oxidation number of oxygen is negative 2 in most compound, but is a negative 1 in peroxide. And the sum of the oxidation number of all atoms in a molecule or ion must be equal to the total charge of the molecules or ion. For example, the oxidation number of sulfur in a sulfate ion can be calculated as the following. Oxygen has the oxidation number of negative 2 and there are 4 oxygen atoms in a sulfate ion. So, the total oxidation number of the oxygen atom is negative 8. Sulfur has an oxidation number of X and the total charge of the sulfate ion is negative 2. So we have the equation of X minus 8 X negative 8 equals 2 and negative 2. Solving for the X, we can get X equals plus 6 and therefore positive 6. Therefore, the oxidation number of sulfur in the sulfate ion is positive 6. Move on to the constant oxidation state of atoms, molecules, and ions. So, the oxidation number of an atom is a number assigned to the atom in a chemical compound that represents the number of electrons that the atom has lost, gained, or shared. The oxidation number can be positive, negative, or 0. Atoms or molecules and ions that have constant oxidation state are those who have those atoms have the same oxidation state in all of their possible compounds. For example, chlorine. Chlorine has an oxidation state of negative 1 in all of its compounds. This is because chlorine is always found in nature as a chlorine ion, Cl. So, the oxidation state of the atom is a homopolar molecules are 0. This is because homopolar molecules are formed by the sharing of electrons between atoms of the same elements. For example, the oxidation state of each oxygen atoms in our oxygen molecules is 0. And the oxidation state of charged ion is equal to the net charge of the ion. This is because the charged ions are formed by the loss or gain of electrons by atom. For example, oxidation state of sodium ion is a positive one because sodium has lost one electron to form the ion. As you can see here is a table of oxidation state of some common elements. So elements, we have alkaline metals, which has the oxidation state of positive 1. Alkaline earth metals, which has the oxidation state of positive 2. Now we have also here the boron family metals, which have the oxidation state of positive 3. Also we have the elements of hydrogen, where is positive 1 in a compound with non-metals, but is negative 1 in compound with metals. And lastly, we have the elements of oxygen, which is negative 2 in the most compound and also negative 1 in peroxide. So that's all. I hope you learned from the discussion, and thank you for listening.
Good morning and welcome to Channel 1. I am Liezly Entera, your weather presenter for today. And for today, July 24, the temperature in the morning here in Davao is 25 degrees Celsius. If we take into account factors such as wind, humidity, and other weather conditions, the temperature can feel like 27 degrees Celsius. The wind blows at 5 km per hour. At noontime, the temperature is 30 degrees Celsius. The humidity will be around 69% with a wind speed of 8 km per hour. And at the evening, there will be a 70% chance of rain. We have a good weather for today, and today is a perfect day to learn about the oxidizing and reducing agents. Oxidizing and reducing agents are key terms used in describing the reactants in a redox reactions that transfer electrons between reactants to form products. An oxidizing agent or oxidant gains electrons and is reduced in a chemical reaction. Also known as the electron acceptor, the oxidizing agent is normally in one of its higher possible oxidation states because it will gain electrons and be reduced. Examples of oxidizing agents include halogens, potassium nitrate, and nitric acid. On the other hand, a reducing agent or reductant loses electrons and is oxidized in a chemical reaction. A reducing agent is typically in one of its lower possible oxidation states and is known as the electron donor. A reducing agent is oxidized because it loses electrons in the redox reaction. Example of reducing agents include the earth metals, formic acid, the sulfide compounds. To help eliminate confusion, there is a mnemonic device to help determine oxidizing and reducing agents. It is OILRIG or OILRIG, and it stands for oxidation is loss and reduction is gain of electrons. An oxidation reaction is a type of chemical reaction in which there is a loss of an electron from one substance. A reduction reaction, to the contrary, is a reaction that supplies an electron to a substance. A redox reaction is a combination of oxidation and reduction reaction in which one of the substance gives up an electron and another substance takes the electron. So we have an example here. In the left side, the reactant Zn is the reducing agent because it loses electrons and is being oxidized. And the reactant Cu is the oxidizing agent because it gains electrons and is being reduced. The reducing agent can be oxidized by losing some of its electrons. The oxidation state increases and is an electron donor. Reducing agent is oxidized during the reaction and is responsible for causing the reduction of another reactant. On the other hand, an oxidizing agent can be reduced by obtaining electrons. The oxidation state of the oxidizing agent decreases and is called the electron receiver. The oxidizing agent is reduced during the reaction and is responsible for causing the oxidation of another reactant. By looking at each element's oxidation state on the reactant side of a chemical equation compared with the same element's oxidation state on the product side, one can determine if the element is reduced or oxidized, and therefore identify the oxidizing and reducing agents of a chemical reaction. In order to identify an oxidizing agent, the information can be grasped from the oxidation number of an atom before and after the reaction. An increase in the oxidation number of the compound towards the product side is because the substance lost electrons and was oxidized. A decrease in the oxidation number of the compound towards the product side is because the substance gained electrons and was reduced. So the substance that is reduced in a reaction is the oxidizing agent because it gains electrons, while the substance that is oxidized in a reaction is the reducing agent because it loses electrons. And that's all for today's weather update and learning oxidizing and reducing agents. Thank you for watching.
Good morning, I'm Ken from XY News. Let's look at our news for today. Headlines of this news: balancing oxidation, reduction by the oxidation number. One way to balance redox reaction is by keeping track electron transfer. By using the oxidation numbers of each of the atoms, for the oxidation number change method, start with the unbalanced skeleton equation. We can identify redox reactions using oxidation numbers, which are assigned to atoms in molecules by assuming that all bonds to the atoms are ionic. An increase in oxidation number during a reaction corresponds to oxidation, while a decrease corresponds to reduction. The following are utilized in the oxidation method for balancing redox reaction. Step 1. Correctly express the redox reaction formula for reactants and products in a chemical reaction. Step 2. Determine the elements that undergo a change in oxidation number in the given reaction by assigning oxidation numbers to the individual elements represented in the reaction. Step 3. To calculate the oxidation number for a molecule or ion in a chemical reaction, look at the number of atoms involved. If the numbers are not equal, you can multiply them together to get a number that makes them equal overall. If two substances only undergo oxidation or reduction, then it suggests a problem with the chemical reaction. This means that one of the formulas for the reactants or products may be incorrect. It may also mean that the assignment of oxidation states is incorrect. Step 4. If the process takes place in water, keep in mind that it involves ions. As a result, add H plus or OH ions to the appropriate side of the reaction. The ionic charges of the reactant and products will be equivalent in the end. If the reaction occurs in the acidic solution, H plus ions should be included in the chemical equation. In the same way, if the reaction occurs in a basic solution, add OH ions to the chemical equation. Step 5. The numbers of hydrogen atoms on each side of the equation must be equalized by adding water molecules or H2O molecules. It is important to double check the oxygen atoms in the equation. If there are equal number of oxygen atoms presented on both the reactants and the product side, the reaction is called a balanced reaction. By solving a problem using the oxidation number approach, the learners can get a better understanding of the procedures involved in balancing redox reaction. In this video, we're gonna learn how to use oxidation numbers to balance a redox reaction. Sometimes, when you have trouble balancing equation and it's really complex, it's because it's a redox reaction. So we're gonna learn a method that always works. If it's really simple reaction, you don't need it, but it's useful for some of the more complicated ones. I will do one practice one, and then you do several more in class. Together, this will just get you started. So the first thing is assign oxidation number 0 plus 1 plus 5 minus 2 plus 4 plus minus 2 plus 4 plus minus 2 plus minus 2. And next thing I'm gonna do is I'm gonna identify what two things are changing. Khen is changing and nitrogen is changing. So I'm going to connect them with lines. Just like that. And then I'm going to write on those lines what's happening to the nitrogen goes from plus 5 to plus 4. So it gained 1 electron. Now I can have something gain of 1 electron and something lose 4 electrons. So electrons transferred have to be equal. They are the same electrons. So what I'm going to do is I'm going to make these electrons equal by multiplying by some number and make them equal. So I'm going to multiply the top by 4 and the bottom by 1. And what this number tells me to do is it gives me the coefficient for the equation. That means that there is a 1 in front of the 10 here because there was 1 here. It means that there's a 4 in front of the two compounds that have nitrogen in it. And all I have to do is I have to take any compounds that's now changing, and I have to do it by inspection, in other words by looking at it. But it's usually water and it's pretty simple. If I look here, I have 4 it, so I'm going to put a 2 here. And if you look, you've got 10 and 10, 4H and 4H, 4N and 4N, and 1 this side we got 12 O's, and over here 2 and 8 and 2 is 12 O's. So we have successfully balanced this equation. What's the difference between the oxidation number method and the half reaction method? Chemistry balancing redox reaction using the oxidation number method. There's no real difference between the oxidation number method and the half reaction method. They are just different ways of keeping track of the electrons transferred during the reaction. The only surefire way to balance a redox reaction is to recognize the oxidation part and the reduction part. Then you balance by making the electron loss equal the electron gain. In the oxidation number method, you would determine the oxidation numbers of all atoms. Then you multiply the atoms that you have changed by small whole numbers. You are making the total loss of electrons equals to the loss gain of electrons. Then you balance the rest of the atoms. In the half reaction method, you determine the oxidation numbers and write 2 half reactions. Then you multiply them by small whole numbers to make the loss and gain of electrons equal. Then you add the 2 half reactions together and balance the rest of the atoms. In the both methods, you must know what the oxidation numbers are and what they become during the reaction. Sometimes one method is more convenient than the other method. It's just one process and one method with variation. None of it will happen if you don't get the oxidation number of every player in the reaction. To summarize this topic, an oxidation number is a number that is assigned to an atom in a substance. The oxidation number could be positive, negative, or zero, and it indicates if electrons are lost or gained. In other words, the oxidation number is a number that helps us keep track of electrons in an atom. Oxidation, reduction, reaction are important because they are the principal sources of energy in this planet, both natural or biological and artificial. For that informational news, this is the most commonly used definition of oxidation and reduction and most widely applicable. In this case, oxidation is the loss of electrons and reduction is the gain of electrons.